What if you could hold a piece of the past in your hand, a slender cylinder of rock or ice that contains secrets from millions of years ago? It's not science fiction, it's the reality of core sampling, one of the most powerful and poetic ways we unlock the hidden history of our planet. Every layer in these geological time capsules tells a story of ancient climates, lost worlds, and the slow, majestic forces that have shaped the Earth beneath our feet. In this video, we're going to explore how scientists are piecing together the shattered puzzle of primeval Earth, using these incredible subterranean archives to rebuild landscapes that vanished long before humans walked the surface. It's a journey that takes us from the deepest oceans to the highest glaciers, from the age of dinosaurs to the dawn of civilization, and it all begins with something as simple and as profound as a core sample. These unassuming cylinders of sediment and stone are like pages in Earth's diary, and we're only just learning how to read them. Together, we'll uncover the methods and the mysteries behind this extraordinary science. We'll see how researchers are decoding the stories locked in stone, grain by grain, layer by layer, revealing not just where we've been, but where we might be headed. So settle in and open your mind. By the end of this exploration, you'll see the world and time itself in a whole new light. But where did this incredible technique even come from? The story of core sampling starts not in a high-tech lab, but down in the mines. In the late 19th century, prospectors and miners needed a better way to find out what lay beneath the surface before they invested enormous time and resources into digging. They began using simple manual drills to bring up long, thin cylinders of rock, the very first core samples. This was purely practical. It was about finding valuable minerals and assessing the stability of mine shafts. They were looking for economic gain, not geological history. Yet, in doing so, they inadvertently invented a method that would become the cornerstone of paleoclimatology and historical geology. The early technology was rudimentary. Imagine a hollow drill bit attached to a long series of pipes, rotated by hand or with a simple engine, biting slowly into the earth. As it cut downward, a cylinder of rock would be captured inside the barrel of the drill. When pulled back to the surface, this pristine column preserved the exact order of the rock layers it had passed through. For a miner, a streak of quartz might signal gold, while a layer of soft shale could mean instability. But for a scientist, that same sample held a completely different kind of treasure, a sequential record of time. The real paradigm shift happened when researchers realized this industrial tool could be turned into a scientific time machine. It was the advent of oceanographic expeditions in the mid-20th century that truly unlocked its potential. Scientists like Cesare Emiliani began using piston corers devices that could plunge deep into the ocean floor and retrieve long tubes of soft sediment. These muddy layers, accumulated grain by grain over millions of years, were perfectly undisturbed, offering a continuous climate diary far more complete than any record on land, which is often scoured away by glaciers or erosion. This was the moment core sampling evolved from a prospector's tool into one of humanity's most profound instruments of discovery. The technology advanced rapidly. We developed drills capable of penetrating miles into Antarctic ice sheets, capturing air bubbles from ancient atmospheres. We engineered sophisticated rigs that could operate from the decks of massive ships, drilling into the seabed in water thousands of meters deep. Each technological leap allowed us to reach further back in time, to extract longer and more detailed archives of the planet's past. What began as a simple way to find copper or coal has given us the evidence to understand ice ages, to see the rise and fall of ancient seas and to pinpoint the moment an asteroid struck the Earth. It transformed our relationship with the planet, allowing us to read its history not as a series of disconnected fragments, but as a grand, continuous narrative written in stone, ice, and mud. Think of a core sample not just as a column of rock or ice, but as a book. Each layer is a page, and the entire volume tells a complete story of a specific place across vast stretches of time. This natural archive works on a simple but powerful principle, the law of superposition. In any undisturbed sequence, the oldest layers are at the bottom and the youngest are at the top. It's a chronological stack with millennia of history ordered from the bottom up. A single core can encapsulate a few thousand years of a lake's history or millions of years of deep ocean sediment, offering a continuous record that surface rocks, jumbled by earthquakes and erosion, simply cannot provide. But how do we read these pages? Scientists act as detectives, examining every clue preserved within the strata. They look at the physical composition, the size and type of sediment grains can tell us if the environment was a swift-moving river, a calm deep ocean, or a windy desert. They search for chemical signatures, like specific ratios of oxygen isotopes locked within the shells of tiny marine fossils called foraminifera. These ratios are incredibly sensitive to temperature. By measuring them, researchers can calculate the precise water temperature when that tiny creature was alive, building a detailed record of ocean warming and cooling that stretches back millions of years. Perhaps the most evocative evidence comes from biological remnants. A single grain of pollen, perfectly preserved in the mud of an ancient lake bed, can identify the type of forest that once surrounded it. A fragment of a leaf or the spore of a fern paints a picture of the local ecosystem. In ice cores, the evidence is even more direct. Trapped within the frozen layers are tiny bubbles of atmosphere, sealed under increasing pressure as more snow falls. These are literal samples of ancient air. By cracking open these bubbles in a lab, scientists can analyze the exact chemical composition of the air from a specific year, thousands of years ago, measuring greenhouse gases like carbon dioxide and methane directly. This precise chronological control is what transforms a collection of interesting data points into a coherent narrative. By counting the annual layers in an ice core, much like counting tree rings, scientists can assign a specific year to each data point, creating a timeline with astonishing resolution. They can see not just the broad sweep of an ice age, but a single, particularly harsh winter or a massive volcanic eruption that darkened the skies for a season. This allows them to correlate events across the globe, connecting a period of drought recorded in a cave stalagmite in Asia with a change in ocean currents recorded in a sediment core from the Atlantic. It's this painstaking work of linking clues that lets us rebuild the saga of our planet's transformation, turning scattered fragments into a story we can finally understand. So how do we move from a tube of frozen water or compacted mud to a detailed understanding of a world that existed tens of thousands of years ago? The true magic lies in the chemical and physical fingerprints locked within each layer, silent witnesses to the climate of their time. One of the most powerful tools in this forensic toolkit is the study of oxygen isotopes. It sounds complex, but the principle is beautifully simple. Oxygen comes in different forms or isotopes. The most common is oxygen-16, which is lighter. A heavier, less common form is oxygen-18. When the planet is colder and more water is locked up in massive ice sheets, the lighter oxygen-16 evaporates more easily from the oceans but gets trapped in the growing glaciers. This leaves the ocean water and consequently the shells of tiny marine organisms called foraminifera that form from it, enriched with a higher proportion of the heavier oxygen-18. When those tiny creatures die, their shells settle to the seafloor, becoming part of the sediment record. By drilling a core and meticulously measuring the ratio of these two oxygen isotopes in each layer of fossil shells, scientists can create a precise thermometer, charting the rise and fall of global temperatures and ice volume across millions of years. Ice cores offer an even more direct measurement. As snow falls year after year in places like Greenland and Antarctica, it compresses under its own weight, trapping tiny bubbles of the atmosphere from that exact moment in time. It is quite literally an archive of ancient air. By extracting and analyzing the gases in these bubbles, particularly carbon dioxide and methane, researchers can read the recipe of our planet's ancient atmosphere. The correlation they discovered is both elegant and profound. When you graph the temperature data from the oxygen isotopes against the greenhouse gas data from the bubbles, the lines move in near-perfect lockstep. Warm periods feature high concentrations of CO2. Cold, glacial periods show low concentrations. This undeniable link, written in ice over 800,000 years, provides the most compelling natural evidence for the fundamental relationship between greenhouse gases and planetary temperature. These climate chronicles reveal that Earth's history is not one of stable, tranquil conditions, but a dynamic story of dramatic shifts. The records show the grand, slow dance of ice ages, where the planet cycled between glacial periods with ice sheets covering much of North America and Europe and shorter, warmer interglacial periods like the one we live in now. But perhaps more startling are the abrupt changes, moments where the climate system seems to have flicked a switch. Evidence from ice cores points to instances where average temperatures in Greenland shot up by 10 degrees Celsius or more in just a handful of decades, a geological blink of an eye. These rapid oscillations, likely caused by sudden reorganizations of ocean currents, would have been catastrophic for ecosystems, forcing life to adapt, migrate, or face extinction. This deep time perspective is what makes core samples so critically important for our modern world. They provide the essential context for today's climate change. We can now look at the current rapid rise in CO2, a spike driven by human industry that far exceeds any natural increase found in the ice core record, and understand its potential consequences with terrifying clarity. The ancient past shows us the rules of the game. It demonstrates the sensitivity of Earth systems and the powerful forces that are set in motion when its atmospheric balance is disrupted. By unearthing these ancient climates, we are not just satisfying historical curiosity. We are reading a warning and a lesson from the past, written in mud and ice, that is directly relevant to our future on this planet. But how do we move beyond charts of temperature and gas levels to actually visualize a world that has been lost to time? The true power of core sampling reveals itself when we use these slender cylinders of Earth to perform a kind of geological cartography, mapping landscapes that vanished millennia ago. This is far more than just reading a climate report from the past. It is an act of resurrection, rebuilding entire ecosystems from the subtle clues trapped in sediment. Every layer in a core tells a story not just of what the climate was, but of what the world looked like, the lay of the land, the flow of water, and the life that thrived there. The process is a masterclass in scientific deduction. Geologists begin by examining the very texture of the sediment. The size, shape, and composition of the grains are like a coded message. Coarse, gritty sand and smooth pebbles might indicate the powerful flow of an ancient river channel, tumbling rocks along its bed. In contrast, fine, silty clay points to a calm, low-energy environment like a lakebed or a deep ocean plain, where only the tiniest particles could slowly settle out of the water. By tracking these changes vertically through a core, scientists can trace the evolution of a landscape, watching as a river delta gradually silts up and becomes a swamp, or as a deep lake slowly fills in to become dry land. The biological evidence adds color and life to this physical map. A single layer rich in the pollen of oak and elm trees paints a vivid picture of a dense temperate forest. A sudden shift to pollen from grasses and herbs suggests the opening up of a grassland or meadow. The microscopic shells of diatoms, tiny algae that are hyper-specific to water conditions, can tell researchers if a body of water was fresh or salty, deep or shallow, nutrient-rich or poor. In the most thrilling finds, cores can even capture direct evidence of animal life, a fragment of bone, a beetle's wing case, or the DNA of mammals leached into the soil. Each of these tiny fragments is a piece of a vast puzzle, allowing scientists to infer the topography, hydrology, and ecology of a place that hasn't seen the sun for thousands of years. Perhaps the most stunning example of this is the rediscovery of Doggerland. Today, the North Sea is a cold, tempestuous body of water between the UK and mainland Europe. But by analyzing countless sediment cores extracted from the seafloor, researchers have painstakingly reconstructed a Mesolithic world that was once a vast, low-lying plain, crisscrossed by rivers, teeming with wildlife, and inhabited by early human hunters. The cores revealed not just the peat of ancient marshes and the sand of riverbanks, but also tools, worked wood, and even the footprints of those long-vanished people, preserved in a layer of silt and then sealed beneath the mud of the rising seas. This wasn't just a hypothetical map, it was a detailed reconstruction of a lost homeland, erased by the relentless forces of plate tectonics and glacial melt that caused sea levels to rise and inundate the landscape. Through the humble core sample, a continent that was lost to the waves has been found again, reminding us that the world we know is just a snapshot in time, and that the ground beneath our feet holds the memories of forgotten worlds. The transformation of core sample analysis from a manual, painstaking process to a high-tech scientific revolution is one of the most exciting developments in modern geology. For decades, researchers were limited to what they could see with the naked eye or a standard microscope, carefully splitting open cores and describing the visible layers. While this provided a foundation, it was like trying to understand a complex novel by only reading every 10th page. Today, an entire suite of advanced imaging and analytical technologies allows us to read every single word, and even between the lines, extracting stories from the stone that were utterly invisible just a generation ago. One of the most powerful tools in this new arsenal is the CT scanner, similar to the technology used in hospitals. But instead of looking for a fracture in a bone, scientists use it to peer inside a core sample without ever breaking it open. This non-destructive method creates a detailed three-dimensional X-ray image, revealing internal structures like tiny fossils, mineral veins, or delicate layering that could be destroyed by physical sampling. It allows researchers to digitally slice the core in any direction, examining the intricate architecture of the sediment in perfect, undisturbed detail. This is crucial for preserving these priceless archives for future generations of scientists with even better technology. To understand the chemical secrets locked within those layers, researchers turn to mass spectrometry. This technique is astonishingly precise, capable of measuring the ratios of different isotopes, slightly different forms of the same element, down to the atomic level. Remember those oxygen isotopes that tell us about past temperature? A mass spectrometer is the device that makes those measurements possible. It can detect vanishingly small traces of elements that act as proxies for everything from ocean acidity to the productivity of ancient plankton blooms, translating subtle chemical signatures into a detailed language of past environmental conditions. Perhaps the most mind-bending advancement is the application of paleogenomics, the recovery and sequencing of ancient DNA. We're not talking about cloning dinosaurs. The DNA preserved in sediment cores is often fragmented into tiny pieces and comes from the countless microorganisms, plants, and animals that lived in and around the environment. By extracting this environmental DNA from different layers in a core, scientists can track changes in entire ecosystems over time. They can identify which species of grass dominated a prairie 100,000 years ago, or detect the moment a new microbial community colonized a lake, offering a biological timeline that complements the physical and chemical data with incredible specificity. All of this microscopic data would be just a collection of disjointed facts without the power of computational modeling and remote sensing. Supercomputers can now integrate the information from thousands of cores across the globe, weaving them together with satellite data and global geological maps. This allows scientists to run sophisticated simulations of ancient climates, watching as virtual ice sheets grow and retreat or seeing how ocean currents shifted when a land bridge emerged. Remote sensing from aircraft and satellites helps identify the best locations to drill by revealing subsurface structures over vast areas, guiding the quest for the most informative records. Technology has become the essential bridge, turning a cabinet full of rock cores into a dynamic, interactive model of a lost world, allowing us not just to see the data, but to truly walk through the primeval landscapes of Earth's deep past. To truly grasp the monumental significance of ice core science, we must travel to the vast, frozen expanse of Greenland. Here, under the relentless polar sun and howling winds, an international team of scientists embarked on one of the most ambitious quests in modern history, to drill down through 2 miles of solid ice and pull up a climate record of unparalleled clarity. This was not a simple task. It was a colossal engineering and logistical feat. They had to transport hundreds of tons of equipment to the most remote and hostile environment on the planet, operate a drill in temperatures that could freeze machinery solid, and ensure that the precious cores, once extracted, were kept in a perfect state of deep freeze all the way back to the laboratory. The result of this Herculean effort was the Greenland Ice Core project, and what it revealed would fundamentally reshape our understanding of Earth's climate personality. The ice of Greenland is not a homogeneous block. It is the most meticulously detailed history book imaginable. Each year's snowfall is preserved as a distinct paper-thin layer, compressed by the weight of subsequent winters. By carefully counting these layers, much like counting tree rings, scientists can assign a precise year to every inch of the core, creating a timeline that stretches back over 100,000 years with astonishing annual resolution. But the real magic is locked within the ice itself. As the snow compacted, it trapped tiny bubbles of the ancient atmosphere, sealing them away in a natural time capsule. These are not inferences or proxies in the traditional sense. They are literal, physical samples of the air that ancient humans and woolly mammoths breathed. By analyzing the gases in these bubbles, particularly carbon dioxide and methane, researchers obtained direct, incontrovertible measurements of past greenhouse gas concentrations. The data painted a picture of a climate system that is far from the slow, gradual beast we once imagined. The ice core record revealed that Earth's climate is capable of breathtakingly abrupt and violent shifts. The most startling example is an event known as the Younger Dryas, which occurred around 12,800 years ago. The ice cores show that as the world was steadily emerging from the last ice age, warming into a more temperate period, something dramatic happened. In a geological instant, perhaps as short as a single decade, temperatures in Greenland plummeted by as much as 10 degrees Celsius. This wasn't a minor cold snap. This was a return to near glacial conditions that lasted for over 1,000 years. The cause is still debated, with theories pointing to a sudden halt in the ocean's conveyor belt circulation, potentially triggered by a massive influx of freshwater from melting ice sheets. What the ice cores made undeniably clear was the terrifying speed of change. Ecosystems, ocean currents, and global weather patterns did not have centuries to adapt. They were thrown into chaos almost overnight. Beyond temperature and gases, the ice also acts as a ledger of global cataclysms. Volcanic eruptions anywhere on the planet spew sulfuric acid and fine ash high into the atmosphere, where winds can carry these particles globally. When they eventually fall onto the ice sheets of Greenland, they form a distinct acidic layer in the ice. By matching the chemical fingerprint of these ash layers to known volcanoes, scientists can precisely date eruptions and even discover previously unknown supervolcanic events. This volcanic record is another critical piece of the puzzle, showing how sudden injections of particulates into the atmosphere can shield the Earth from the sun's rays, leading to periods of global cooling and influencing the course of human history, from failed harvests to the fall of civilizations. The Greenland ice cores did more than just provide data. They delivered a profound and humbling lesson. They showed us that the climate system has thresholds, tipping points that once crossed can unleash changes of a scale and speed that are difficult to comprehend. This deep time perspective is what makes these frozen archives so critically relevant today. They provide the essential baseline, the natural rhythm of planetary temperature and gas fluctuations against which we can measure our current human-driven experiment. The unprecedented rapid rise in CO2 that we see in the very top layers of those ice cores stands out like a screaming siren against 100,000 years of natural variability, a stark and sobering reminder that we are pushing the levers of a system capable of dramatic and unpredictable change. While we often think of fossils as the massive bones of dinosaurs or the intricate impressions of ancient leaves, some of the most powerful biological evidence in core samples is almost invisible to the naked eye. These are microfossils, the tiny, incredibly durable remains of microorganisms that once teemed in ancient oceans and lakes. Creatures like foraminifera, single-celled organisms with intricate calcite shells, or diatoms, algae encased in delicate glass-like silica, are the unsung heroes of paleontology. When these tiny beings died, they rained down by the billions onto the seafloor, their minuscule shells piling up layer upon layer, creating a continuous census of ocean life across millions of years. But they are far more than just sediment. Each one is a data point. The specific chemistry of a foraminifera's shell, particularly the ratio of oxygen isotopes locked within its structure, acts as a precise paleothermometer. By analyzing these shells from different depths in a core, scientists can read the exact temperature of the water the creature lived in, charting the warming and cooling of ancient seas with astonishing accuracy. Beyond temperature, the very types of species present tell a detailed story of the environment. Some species of foraminifera thrive only in warm tropical waters, while others are specialists of the cold polar seas. Finding a layer in a deep sea core suddenly rich in a cold water species is a strong indicator that a pulse of frigid water, perhaps from a melting ice sheet, swept through the area. Diatoms are equally eloquent. Their presence alone indicates sunlight and nutrients, but different species are hyper-specialized. Some flourish in salty, open ocean conditions, while others prefer the brackish water of a coastal estuary. A shift in the diatom community within a core can signal a change in sea level, the opening or closing of an ocean gateway, or even a change in ocean circulation patterns that brought new nutrients to the surface. These microscopic organisms are such sensitive recorders that their fossilized remains allow us to reconstruct not just the climate, but the very chemistry and structure of vanished marine ecosystems. On land, the story is written in a different kind of dust, terrestrial cores extracted from the bottoms of ancient lakes or peat bogs contain a microscopic rain of pollen and spores that has fallen for millennia. Every flowering plant produces vast quantities of pollen, each grain uniquely sculpted to identify its parent species. These tiny, tough particles are carried on the wind, settling on the surfaces of lakes and wetlands where they are preserved in the accumulating mud. By washing a sample of this mud through fine sieves and identifying and counting the pollen grains under a microscope, scientists can take a census of the ancient forests and grasslands that surrounded the site. A core showing a dominance of spruce and pine pollen paints a picture of a cold, coniferous boreal forest. A layer suddenly rich in grass and sagebrush pollen indicates the opening up of a dry grassland or steppe. This technique, known as palynology, is so precise that researchers can track the advance and retreat of tree lines with changing temperatures, or even identify the arrival of a new species in a region. The true power of this biological detective work is unleashed when these different lines of evidence are woven together. Imagine a core taken from a coastal sediment basin. The marine microfossils might show a sudden cooling of the water, while at the same time the pollen record from the same layer shows a dramatic increase in grass pollen and a decrease in tree pollen. This correlation tells a compelling story. A cooling climate made the adjacent continent drier, causing forests to shrink and grasslands to expand. Now add another clue, a thin layer of ash from a volcanic eruption found at the same depth, which can be precisely dated. Suddenly, we have not just a story of environmental change, but a precisely dated event that may have triggered it. This interdisciplinary approach allows scientists to move beyond simple observations and start reconstructing cause and effect, seeing how a change in ocean temperature influenced rainfall on land, which in turn dictated what plants could grow and what animals could survive. These biological clues do more than just fill in data points on a chart. They perform the ultimate act of scientific resurrection. A sterile layer of gray mud in a core sample transforms into a vibrant, sun-dappled Cretaceous sea, swarming with ammonites and the early ancestors of today's fish. A band of dark peat becomes a humid Carboniferous swamp, echoing with the calls of giant dragonflies and shaded by towering ferns. By listening to the whispers of pollen and the stories told in microscopic shells, we can people these lost worlds, understanding the dynamic and deeply interconnected dance between life and its environment. This narrative, written in biology and sealed in stone, shows us that life is not just a passive passenger on a planet rocked by geological forces, but an active and responsive participant, constantly adapting, migrating, and evolving in the face of a forever changing Earth. While the biological and chemical clues in core samples tell us about the environments of the past, the physical structures within the rock itself reveal something even more fundamental: the titanic, slow-motion ballet of the Earth's crust. When we pull up a core from a mountain range or an ocean basin, we are not just looking at a stack of layers, we are reading a strain gauge that has recorded immense forces. The very architecture of the rock, the way it is bent, broken, and folded, provides direct physical evidence of the earthquakes, collisions, and uplifts that have sculpted our planet's surface over hundreds of millions of years. Imagine a core sample that shows a clean, horizontal sequence of sandstone, then shale, then limestone, a straightforward story of an ancient seafloor. Then suddenly that orderly sequence is interrupted. The layers are no longer flat, they are tilted at a sharp angle or bent into a tight, graceful fold. Perhaps there's a clean, sharp line cutting diagonally across the layers, a fault where one section of rock has violently slid past another. These deformations are the frozen in-time signatures of incredible stress. A fold might record the slow, relentless pressure of two continents colliding, crumpling the crust like a rug pushed against a wall. A fault is the scar of a sudden, catastrophic release of energy, an earthquake from a time before humans walked the earth. By carefully studying the orientation and style of these structures, geologists can work backwards to calculate the direction and magnitude of the forces that created them, turning a fractured core into a detailed report on ancient tectonic events. Perhaps the most elegant and conclusive evidence for plate tectonics didn't come from mountains, but from the seemingly featureless abyssal plains of the deep ocean. As new oceanic crust is formed at mid-ocean ridges, the iron-rich minerals in the molten rock align themselves with the Earth's magnetic field like tiny compass needles as the rock cools and solidifies. The fascinating thing is that our planet's magnetic field has reversed its polarity hundreds of times throughout history. What was magnetic north becomes south, and vice versa. When scientists began pulling up core samples from the ocean floor, they discovered something astonishing. The oceanic crust was not a magnetic blank slate, it was a tape recorder. It displayed a symmetrical pattern of magnetic stripes running parallel to the mid-ocean ridges. On one side of the ridge, a stripe of rock would have normal polarity, matching today's field. Right next to it would be a stripe with reversed polarity. This pattern was mirrored perfectly on the other side of the ridge. This could only mean one thing. New crust was being continuously formed at the ridge and then slowly pushed outward, carrying its magnetic timestamp with it like a geological conveyor belt. This single discovery, read from the subtle magnetic signatures in countless core samples, was the final, irrefutable proof that validated the theory of plate tectonics, transforming our understanding of the Earth from a static globe into a dynamic, ever-changing jigsaw puzzle. This ability to date and quantify tectonic movements allows us to perform staggering acts of reconstruction. We can now trace the journey of a continent across the globe. Cores taken from different regions show distinct sequences of magnetic polarity and unique fossil assemblages that act like latitude markers. By matching these sequences, we can piece together the ancient jigsaw of supercontinents like Pangaea or Rodinia, understanding not just where the continents were, but how their collisions raised Himalayan-scale mountain chains and their separations opened vast new oceans. The opening of such ocean gateways had profound consequences. When South America finally split from Antarctica and the Drake Passage opened, it allowed the formation of the relentless Antarctic circumpolar current, which isolated the southern continent in a frigid embrace and led to the formation of its massive ice sheets, dramatically altering the entire planet's climate and ocean circulation. This deep historical perspective is not merely an academic exercise, it is vital for our future. The same tectonic forces that assembled ancient supercontinents are still at work today. By studying the frequency and intensity of past events recorded in rock cores, the evidence of major earthquakes along fault zones, the history of volcanic eruptions in seismically active regions, we can better understand the cycles of these natural hazards. This knowledge helps us assess risk, inform building codes, and prepare for the inevitable geological events that will shape the human world. The slow grind of plates, documented in a cylinder of rock, reminds us that we live on a planet that is very much alive, and that its most powerful movements are often written in the smallest of details. To understand the stories locked within these sediments, we must first learn to read their language. It begins with something as simple as grain size. Picture the difference between trying to walk quickly through a bed of coarse, shifting pebbles on a beach versus sinking slowly into the fine, oozing mud of a deep lake bottom. That same principle applies over geological time. When a core sample reveals a layer of coarse, gritty sand with well-rounded pebbles, it's a strong indicator of a high-energy environment. This is the kind of material that can only be moved and shaped by powerful, persistent forces. Think of the relentless push and pull of waves on a shoreline or the strong, churning flow of a river channel. These environments are dynamic and constantly shifting, and the sediment they leave behind reflects that robust energy. In stark contrast, a section of core composed of extremely fine, smooth clay or silt tells a completely different tale. These tiny particles are so minute that they can remain suspended in still water for days before finally settling. Their presence signifies a calm, low-energy environment where the waters were deep and tranquil. This is the quiet, patient accumulation of the abyssal plain at the bottom of the ocean, the still depths of a large lake, or the protected waters of a lagoon. Here, the sediments settle layer by thin layer, creating a fine-grained record that can capture incredibly detailed, seasonal information, much like the pages of a delicate, ancient manuscript. But the story doesn't end with grain size. The very structures within the sediment layers add another layer of rich detail. Sometimes, when a core is carefully split open, scientists find not flat, horizontal lines, but delicate, curved patterns known as cross-bedding. These are the preserved faces of ancient sand dunes or subaqueous ripples. The angle and direction of these curves act as a fossilized wind vane or current meter, telling researchers precisely which way the wind was blowing across a desert or how a river current was flowing millions of years ago. Similarly, the presence of ripple marks, small, wave-like undulations on the surface of a layer, can distinguish between ripples formed by flowing water and those sculpted by wind, further refining the picture of the past environment. Other subtle features provide even more clues. A layer that contains a mix of chaotic, unsorted sediment with everything from fine clay to large boulders might point to the powerful, grinding action of a glacier. As a glacier advances, it scours the landscape beneath it, pulverizing rock and carrying the jumbled mixture along before depositing it as a moraine when the ice retreats. Even the color and mineral composition of the grains have a story to tell. A reddish or yellowish hue often indicates the presence of iron minerals that rusted in an oxygen-rich terrestrial environment, like a desert or floodplain. A dark gray or black color, however, might signal organic-rich sediments that accumulated in oxygen-poor waters, where decay was slow and plant matter was preserved. By synthesizing all of these clues, grain size, sedimentary structures, color, and composition, a sedimentologist can move from analyzing a simple tube of dirt to reconstructing a vibrant, lost world. A single core might tell a multi-chapter story. It might begin with a chapter written in coarse river sands, evidence of a mighty waterway carving through the land. This might be overlain by a chapter of fine lake clays, indicating the river slowed and spilled out into a vast, peaceful lake. That lake chapter might itself be capped by a layer of volcanic ash, a dramatic event that fell from the sky, followed by a return to river sands as the landscape filled in and the waterway reclaimed its course. This branch of geology transforms the mundane into the magnificent, allowing us to read the epic sagas of erosion, transportation, and deposition that have tirelessly sculpted our planet's surface across millions of years. But with all these incredible stories waiting to be read, we face a fundamental question. When did all of this actually happen? A beautifully preserved layer of pollen or a set of perfectly folded rocks is fascinating, but without a date attached to it, it's just a scene without a timestamp. It could be 100,000 years old or 100 million. This is where the science of geochronology comes in, providing the essential clock that allows us to place these events on a precise timeline, transforming a collection of interesting clues into a coherent historical narrative. The methods scientists use are as diverse as the materials they study, each one a unique key for unlocking time. For events in the more recent geological past, particularly those involving once living things, radiocarbon dating is the most famous tool in the toolbox. It works on a beautifully simple principle. All living things absorb carbon from their environment, including a tiny, unstable fraction known as carbon-14. When an organism dies, it stops taking in new carbon, and that carbon-14 begins to decay at a very steady, predictable rate. By measuring how much carbon-14 is left in a piece of wood, a bone, or a shell found within a core sample, scientists can calculate how long ago that organism died. This technique is incredibly powerful for dating organic materials up to around 50,000 years old, allowing us to pinpoint the timing of events like the extinction of mammoths or the arrival of humans in a new continent with remarkable precision. But Earth's history stretches back billions of years, far beyond the reach of carbon-14. To date these ancient chapters, geologists turn to other radioactive clocks with much longer half-lives. One of the most important is uranium lead dating. The mineral zircon, which forms in molten volcanic rock, naturally incorporates uranium atoms into its crystal structure but strongly rejects lead. This means that when a zircon crystal first forms and cools, it contains uranium but essentially no lead. From that moment on, the uranium begins its slow, inexorable decay into lead. By meticulously measuring the ratio of uranium to lead within a single zircon crystal from a volcanic ash layer in a core, scientists can determine the exact moment that crystal solidified. This gives them an absolute age for that volcanic eruption, effectively placing a bold, unambiguous timestamp in the geological record that can be used to anchor all the layers above and below it. This method can date rocks that are billions of years old, providing the foundation for our entire geological timescale. Not every layer contains a handy volcanic ashfall or a piece of organic material. For the vast stretches of sedimentary rock that make up most core samples, scientists often rely on relative dating techniques. The most fundamental of these is stratigraphy itself, the simple, powerful logic that in an undisturbed sequence, the layers at the bottom are older than the layers at the top. It's the first principle of reading the rock record. When combined with paleomagnetism, the record of Earth's magnetic reversals preserved in the rock, this becomes even more powerful. Scientists have constructed a detailed timeline of when the magnetic field was in normal or reversed polarity. By extracting a core and measuring the magnetic orientation of its minerals down its entire length, they can match the pattern of flips they find to the global reference pattern, much like matching a barcode. This tells them the relative age of each section and allows them to correlate their core with others from across the globe that share the same magnetic signature, even if they are thousands of miles apart. For more recent sediments, particularly from the last few 100,000 years, a fascinating technique called luminescence dating comes into play. It doesn't date the sediment itself, but rather the last time it was exposed to sunlight. Minerals like quartz and feldspar store energy from natural background radiation from the moment they are buried and shielded from light. This energy builds up in their crystal lattice over time. In a dark lab, scientists can stimulate these grains with light or heat, causing them to release that stored energy as a faint glow of light, a luminescence. The brighter the glow, the longer the grains have been buried. By measuring this signal, researchers can determine when a sand dune formed, when a river deposited its sediment, or when a glacier retreated, leaving behind a blanket of till. This technique is perfect for dating events that other methods can't touch, providing a clock for the very act of burial. The true power of these techniques is realized not in isolation, but when they are woven together. A single core might be dated using radiocarbon for its top layers, matched to the global magnetic reversal pattern for its middle sections, and anchored by a uranium lead date from a volcanic ash layer near its base. This cross-validation creates a robust, defensible chronology, a reliable timeline upon which the entire story of the core can be hung. It is this precise dating that allows a scientist to state with confidence that a period of abrupt cooling began 12,800 years ago, or that a mass extinction event occurred 66 million years ago. It turns a chaotic jumble of rock into an ordered series of chapters and verses, allowing us to read the history of our planet not as a vague legend, but as a precise and dated chronicle, giving time its true meaning and context in the epic story of the Earth. Now, to truly appreciate the evidence locked in these cores, we need to understand one of the most elegant and convincing pieces of the plate tectonics puzzle, the story told by paleomagnetism. This fascinating field of study transforms ordinary-looking rocks into ancient compasses, each one faithfully recording the direction of Earth's magnetic field at the moment it formed. It all comes down to tiny, iron-rich minerals like magnetite. When volcanic rock is molten or when magnetic particles are settling through water to form sedimentary layers, these minerals act like countless tiny needles in a compass, freely aligning themselves with the planet's magnetic field. The incredible part happens as the rock solidifies or the sediment lithifies, locking those minerals in place and preserving a permanent, unchangeable record of the magnetic field's orientation at that exact location and moment in time. It's a snapshot of where magnetic north was, frozen in stone. The plot thickens dramatically when we learn that Earth's magnetic field is not a constant, stable force. Throughout our planet's history, its magnetic poles have completely reversed hundreds of times. What we call magnetic north today was magnetic south in the past. Geologists have painstakingly mapped the timeline of these reversals, creating a detailed barcode of normal and reversed polarity periods that stretches back millions of years. When scientists began analyzing the paleomagnetic signatures in core samples drilled from the ocean floor, they discovered something that would become the smoking gun for continental drift. The oceanic crust on either side of mid-ocean ridges displayed a stunningly symmetrical pattern of magnetic stripes. Parallel bands of rock showed normal polarity, then reversed polarity, then normal again, and this identical pattern was mirrored perfectly on the opposite flank of the ridge. This symmetrical pattern could only mean one thing: new oceanic crust was being continuously created at the ridge and then slowly pushed outward, carrying its magnetic timestamp with it like a geological conveyor belt. This single discovery provided irrefutable physical proof that the seafloor was spreading, a key mechanism of plate tectonics. Beyond proving the movement of plates, this magnetic record allows us to become master navigators of deep time, charting the incredible journeys of the continents themselves. By measuring the preserved magnetic direction in a core sample from a specific rock layer, scientists can calculate the ancient latitude at which that rock formed. The angle or inclination of the magnetic minerals tells them how far from the pole the rock was located. A shallow angle points to a tropical latitude, while a steep, near-vertical alignment indicates a location close to the pole. This is how we know, for instance, that parts of what is now chilly, temperate England were once located near the equator, basking in a tropical climate, and have since drifted thousands of miles northward. This data is absolutely crucial for accurately interpreting past climates found in core samples. A layer showing evidence of a tropical reef might be confusing if you assume the continent was always in its current position. But when paleomagnetism reveals that continent was actually straddling the equator at the time, the environmental evidence suddenly makes perfect sense. Paleomagnetism does more than just map latitude. It can also reveal a continent's rotation. The declination, or the horizontal angle between magnetic north and true north recorded in the rock, indicates the direction a continent was facing. By analyzing a sequence of layers in a core, researchers can trace the gradual rotation of a landmass over millions of years, watching as it slowly twists and turns on its long voyage across the globe. This ability to reconstruct not just location but also orientation allows us to create increasingly sophisticated and accurate maps of the ancient world, showing the slow, majestic dance of the continents as they assembled into supercontinents like Pangaea and then fragmented into the world we know today. It turns a simple cylinder of rock into a detailed flight recorder, charting the course of a continent's entire geological lifetime. While the ice sheets of Greenland offer a pristine and detailed climate record, some of the most comprehensive and continuous archives of Earth's history lie at the bottom of the ocean, buried beneath miles of water. To access these deep time diaries, humanity embarked on one of its most ambitious and sustained scientific endeavors, the international effort of ocean drilling. This monumental project, spearheaded today by the International Ocean Discovery Program, represents a floating university of scientists, engineers, and crew who sail the globe on a mission to extract Earth's memory from beneath the seafloor. Their tool is a massive drill rig mounted on a specialized ship, capable of lowering a drill string through kilometers of ocean water and then penetrating hundreds of meters into the seabed to retrieve core samples from the deepest and most ancient sediments on the planet. The value of these marine archives is almost unparalleled because of one simple, profound fact. The deep ocean floor is one of the most stable and undisturbed environments on Earth. Unlike continental surfaces, which are constantly scoured by wind, rain, glaciers, and life, the abyssal plains accumulate sediment in a slow, steady, and continuous rain. For millions of years, a gentle snow of microscopic shells, dust from distant continents, and ash from volcanic eruptions has settled onto the seafloor, layer upon delicate layer, creating a perfect chronological record of global change. There are no rivers to churn up the mud, no earthquakes to jumble the sequence, just the patient, relentless accumulation of time itself, preserved in the deep, dark quiet. This allows scientists to obtain cores that provide an almost unbroken timeline, stretching back over 170 million years in the oldest oceanic crust. What these cores have revealed is nothing short of a rewrite of Earth's history book. Within the layers of soft ooze and hardened mud, researchers have found the unmistakable calling cards of global catastrophes. A thin, global layer of iridium-rich clay, found in ocean cores from the Pacific to the Atlantic, provided the crucial evidence for the asteroid impact that triggered the mass extinction of the dinosaurs 66 million years ago. This same layer is also filled with tiny, glassy spherules, frozen droplets of molten rock thrown into the atmosphere by the impact, and soot from the worldwide wildfires that followed, painting a horrifyingly vivid picture of that fateful day and its long, dark aftermath. Beyond single events, these marine sediments track the slow, tectonic dance of the continents and its profound impact on global climate. As continents rift apart or collide, they open and close critical ocean gateways, seaways that can completely alter the planet's circulatory system. Cores drilled in the Atlantic Ocean, for instance, trace the story of the Gulf Stream. By analyzing fossil assemblages and sediment types, scientists determined when the narrow seaway between North and South America finally closed, diverting warm equatorial waters northward and giving birth to the powerful current that now moderates Europe's climate. Similarly, cores from the Southern Ocean document the separation of South America from Antarctica, an event that allowed the frigid, relentless flow of the Antarctic circumpolar current to form, effectively isolating the southern continent in a deep freeze and triggering the formation of its massive ice sheets. The resolution of these records is so fine that they can even chronicle recurring climate phenomena. In the Pacific Ocean, cores taken from the seabed near Peru contain layers that tell the history of El Niño events over thousands of years. During an El Niño, changes in ocean currents and water temperature affect the types of microorganisms that thrive and die, leaving a distinct chemical and biological signature in the sediments they become. By reading these signatures, researchers can reconstruct the frequency and intensity of El Niño cycles deep into the past, revealing how they have responded to changes in Earth's baseline climate and providing critical context for understanding their behavior in our warming world. These deep sea cores are more than just a record of the past. They are a mirror reflecting the interconnectedness of Earth's systems. A volcanic eruption in Indonesia leaves a layer of ash in the Indian Ocean. A period of intense drought in Africa sends a pulse of distinctive dust into the Atlantic. The growth of ice sheets in the Northern Hemisphere changes the chemistry of the entire global ocean, recorded in the shells of tiny creatures everywhere. Each core is a single thread, but when woven together with hundreds of others from across the world's oceans, they form a magnificent tapestry that shows how atmosphere, ocean, ice, and rock are all inextricably linked in a single, dynamic planetary system. While the climate records from ice cores are revolutionary in their own right, these frozen cylinders hold secrets that extend far beyond temperature and greenhouse gases. They are, in essence, the most pristine environmental monitoring stations ever devised by nature, capturing a breathtakingly detailed log of everything that was in the atmosphere at the time each layer of snow fell. Beyond the climate data, these archives preserve the chemical fingerprints of global events, both natural and human-made, creating a timeline of our planet's environmental health and humanity's growing influence upon it. One of the most direct and startling pieces of evidence comes in the form of ancient pollution. It's a common misconception that industrial-scale environmental impact is a purely modern phenomenon. The ice cores tell a different story. Within the layers that date back to the height of the Roman Empire, scientists have found distinct spikes in lead concentrations. This lead did not occur naturally in such quantities. It is the unmistakable signature of extensive silver smelting. The Romans extracted silver from lead ore on an industrial scale to mint their currency, and the resulting lead pollution was carried by the winds across Europe and eventually deposited on the ice sheets of Greenland. The record is so precise that it shows declines in lead pollution during periods of political instability and plague, when economic activity and mining slowed, and then spikes again when the empire regained its strength. This isn't just a climate record, it's a frozen economic report card and a stark reminder that human civilization has been altering the chemistry of the atmosphere on a continental scale for thousands of years. This record of human activity continues through the centuries. A different kind of spike appears in ice cores around the start of the second millennium, this time in methane gas. This increase correlates perfectly with the expansion of rice cultivation in vast flooded paddies across Asia, which produce methane in large quantities. Later, during the Black Death in the 14th century, that methane signal temporarily dips, reflecting the devastating population collapse in Europe and the subsequent reduction in agricultural output and the regrowth of forests on abandoned farmland. The ice even records the massive adoption of the internal combustion engine. Cores from glaciers around the world show a dramatic rise in lead concentrations again in the mid-20th century, corresponding to the use of leaded gasoline, and then a sharp decline after it was phased out due to health concerns. These layers are an undeniable ledger of our species' progress, our mistakes, and our occasional corrections, all written in the subtle chemistry of ancient snowfall. Beyond human history, the ice cores are also our most detailed log of Earth's volcanic past. Every major eruption, from Thera to Tambora, blasts immense quantities of sulfuric acid and fine ash high into the stratosphere, where winds can distribute these particles across the entire globe. When they eventually fall out of the atmosphere, they land on the ice caps, forming a sharp, acidic layer that is perfectly preserved. By analyzing the chemistry of these tiny volcanic shards, scientists can often match them to a specific volcano, creating a precisely dated timeline of its eruptions. This record is far more complete than any historical document, revealing previously unknown super-eruptions that must have caused years of global cooling and failed harvests, potentially influencing the course of ancient civilizations. The volcanic layers also serve as crucial marker horizons, like bolded timestamps in the ice core record, allowing scientists to synchronize cores from Greenland and Antarctica with incredible accuracy, ensuring that the climate story from one pole can be directly compared to the other. Perhaps the most futuristic frontier of ice core science lies in the field of paleogenetics. The ice is not entirely sterile. Trapped within it are ancient bacteria and viruses, preserved in a state of suspended animation for tens or even hundreds of thousands of years. By carefully drilling into the ice and extracting samples under ultra-clean conditions, geneticists can sequence the DNA of this ancient microbiota. This doesn't mean we're at risk of unleashing a prehistoric plague. The vast majority of this genetic material is fragmented and comes from organisms that are long extinct. But for scientists, it's a gold mine. This genetic debris allows them to reconstruct ancient ecosystems in ways never before possible. They can track how microbial communities on the ice sheets themselves changed as the climate warmed and cooled, or identify the types of plants and animals that were living on nearby continents based on the DNA they released into the atmosphere. It opens a window into the very tree of life, showing us how evolution has proceeded in the frozen realms and giving us a baseline to understand how modern climate change might alter these delicate biological communities. The ice core, therefore, is more than an archive of Earth's physical past. It is a frozen library of life itself, holding stories we are only just beginning to learn how to read. But the Earth's geological memory doesn't just record the slow and steady processes of climate and tectonics. It also preserves the echoes of sudden, violent catastrophes that have dramatically reshaped the course of life itself. Within the seemingly peaceful layers of sediment and ice, scientists have discovered the unmistakable forensic evidence of apocalyptic events, asteroid impacts, and supervolcano eruptions that plunged the planet into chaos. These are not myths or speculations, they are hard facts etched into the very fabric of the core samples we pull from the ground, providing a sobering record of our planet's capacity for sudden, violent change. One of the most famous and pivotal discoveries came from a thin, global layer of clay that marks the boundary between the Cretaceous and Paleogene periods, around 66 million years ago. Geologists working on cores from around the world noticed that this specific layer, which coincides with the sudden extinction of the dinosaurs and countless other species, was extraordinarily rich in the element iridium. Iridium is incredibly rare in the Earth's crust but is much more common in certain types of asteroids. The presence of this iridium anomaly in cores from Italy, Denmark, the ocean floor, and countless other sites was the first major clue pointing to an extraterrestrial impact. This discovery, made by analyzing the chemical composition of sediment cores, led directly to the identification of the massive Chicxulub crater buried beneath the Yucatan Peninsula in Mexico. The story the cores tell is terrifyingly vivid. The initial layer of iridium-rich dust is often followed by a layer of tiny, glassy spherules tektites. These are droplets of molten rock that were blasted into the atmosphere by the force of the impact, which then cooled and solidified into glass before raining down across the entire planet. In some marine cores, this is capped by a layer of soot, evidence of the global wildfires that would have raged in the aftermath, ignited by the incendiary re-entry of superheated debris. A single core sample, a few centimeters thick, thus encapsulates the minutes, days, and years following one of the most devastating days in Earth's history. Ice cores provide an equally stark record of a different kind of catastrophe, the colossal volcanic eruptions known as flood basalts or supervolcanoes. While an impact brings death from above, these events unleash hell from below. When a supervolcano like Toba in Indonesia or the more recent Tambora erupts, it doesn't just spew local lava, it injects immense quantities of sulfur dioxide gas high into the stratosphere. This gas rapidly converts into tiny, reflective sulfate aerosols that form a hazy veil around the entire planet, blocking incoming sunlight and causing rapid, dramatic global cooling. In an ice core, these eruptions leave an undeniable signature, a sudden, sharp spike in sulfate concentrations. By measuring the height and width of this sulfate peak, scientists can estimate the sheer magnitude of the eruption and its climatic impact. The ice core record from Greenland shows that the eruption of Tambora in 1815 was responsible for the infamous year without a summer, a period of global famine and hardship. Even more ancient eruptions, like that of Toba around 74,000 years ago, left a sulfate layer so massive that it suggests the event may have triggered a volcanic winter lasting a decade, potentially creating a genetic bottleneck in early human populations. What makes the core sample record so invaluable is that it allows us to move beyond studying single, famous events and instead assess the overall frequency and pattern of global catastrophes. By examining cores from different parts of the world, researchers can build a timeline of these disaster layers. This reveals that while civilization-altering eruptions like Tambora occur every few hundred years, truly cataclysmic, extinction-level events like Chicxulub are thankfully much rarer, happening on scales of many millions of years. This long-term perspective is crucial for modern risk assessment. It helps us understand the statistical likelihood of such an event occurring in our lifetime and informs efforts to monitor near-Earth asteroids or restless volcanic calderas like Yellowstone. The core samples provide the hard data we need to prepare for possibilities that were once the realm of science fiction. Ultimately, these catastrophe layers frozen in time serve as a profound and humbling reminder. They show us that the Earth's history is not a smooth, predictable path, but a story punctuated by sudden, violent upheavals. The comfortable stability we enjoy today is, in a geological sense, a fleeting moment. The planet's climate and ecosystems can be pushed past a tipping point with shocking speed, whether by a rock from space or a rupture in the crust. The thin, dark lines of iridium and sulfate in otherwise ordinary cores are permanent memorials to these events, reminding us of our planet's inherent volatility and the fragile balance that sustains the world as we know it. But the story of our planet isn't just written in ice ages and asteroid strikes. It's also a story about us, core samples have become a remarkable tool for historians and archaeologists, offering a deep time perspective on the intimate and often dramatic relationship between human civilization and the environment. By turning their drills on more recent sediments from lakebeds, bogs, and river deltas, scientists can extract a detailed log of our own history, one that reveals how our ancestors shaped the land and how the land, in turn, shaped the course of our societies. This isn't just geology, it's a new kind of archaeology where the artifacts are not pottery shards or tools, but invisible chemical signals and microscopic particles that tell a story of expansion, collapse, and transformation. Consider the humble grain of pollen. As we've seen, it can reconstruct an entire forest, but it can also chart the rise of agriculture. A sediment core taken from a lake in Europe might show a sudden, dramatic shift in the pollen record. For thousands of years, the layers are dominated by pollen from towering trees like oak, elm, and lime, a signature of a pristine, wild woodland. Then, at a depth that correlates with the arrival of Neolithic farmers, the record changes abruptly. Tree pollen plummets, replaced by a surge in pollen from cereal grains like wheat and barley, and from hardy weeds like plantain that thrive in disturbed, open ground. This shift is the invisible archaeological footprint of the first farmers, a permanent mark in the mud showing the moment they began clearing the ancient forest to plant their crops. The very landscape was being rewritten by human hands, and the core sample captures that revolution in stunning detail. Another powerful piece of evidence comes from microscopic particles of charcoal. When people burn wood, whether for warmth, cooking, or to clear land, they send countless tiny charcoal fragments into the air, which eventually settle into nearby lakes and bogs. A core sample with a sudden, intense spike in charcoal particles signals a major fire event. While a single spike could be a natural wildfire, a sustained increase over centuries is a clear indicator of human activity, the systematic use of fire to manage landscapes. In the Amazon rainforest, cores have revealed that large areas we once thought were pristine wilderness actually show evidence of widespread, managed burning and soil enrichment by indigenous populations centuries before European contact, suggesting the landscape was actively shaped and cultivated, blurring the line between wild nature and human garden. Perhaps the most direct link to human industry comes from the record of heavy metals and pollutants. We saw how ice cores recorded Roman lead smelting, but the same story is written in lake sediments closer to the source. A core from a peat bog in Spain or Britain might show a dramatic increase in lead concentrations starting around 2,000 years ago, coinciding with the expansion of the Roman Empire. The levels might then fall during the empire's decline, only to spike again during the Industrial Revolution with the burning of coal. More recently, the 20th century leaves an unmistakable signature of plutonium and other radioactive isotopes from atomic bomb tests, creating a perfect global timestamp in nearly every sediment core around the world. These layers are an undeniable chemical autobiography of human progress, marking our transition from simple farmers to an industrial and nuclear-powered species. This interdisciplinary approach, blending geology with history, allows us to see the feedback loops between environment and civilization with incredible clarity. A fascinating example comes from cores extracted from the Nile Delta. The annual flooding of the Nile was the lifeblood of ancient Egypt, depositing rich, fertile silt that sustained its agriculture for millennia. By analyzing these silt layers, scientists can see periods of strong, reliable flooding that supported population growth and the construction of grand monuments. They can also identify periods of weak floods or drought, which often correlate with times of famine, political unrest, and the collapse of dynasties. The core doesn't just tell us about the river, it tells us about the fate of pharaohs, showing how the stability of an entire civilization was tethered to the whims of a geological process. Similarly, cores from across Europe document the cataclysmic impact of the Black Death in the 14th century. The historical records tell of a population decimated by plague, and the sediment cores provide the physical proof. Layers of pollen from that time show a dramatic decline in grains like rye and wheat, reflecting the abandonment of farm fields as the labor force vanished. At the same time, tree pollen surges, showing that forests began to reclaim the untended land. This regrowth actually pulled significant amounts of carbon dioxide from the atmosphere, a dip that is recorded in ice cores from Antarctica. It's a staggering connection. A microbial event that killed millions of people on one continent left a measurable mark on the global atmosphere, all because of how it changed land use. This deep time context is what makes these records so vital for our modern world. They show us that humans have been a dominant geological force for thousands of years, not just since the Industrial Revolution. They reveal the long-term trends of soil erosion, deforestation, and pollution that began with our earliest civilizations. By understanding how past societies succeeded or failed in their relationship with the environment, we gain not just historical insight, but practical wisdom for navigating the environmental challenges of our own future, seeing our place in a story that is still being written. This is where core sample analysis transcends mere data collection and becomes an act of true creation, a scientific form of world building. Paleoecologists are the ultimate synthesizers, taking the fragmented clues, the chemical whispers from isotopes, the silent testimony of microfossils, the physical language of sediments, and weaving them together into a dynamic, functioning model of a lost world. They move beyond asking, what was the temperature? Or what plants grew here? To answer far more profound questions, how did energy flow through this ecosystem? Who ate whom? How did these species interact to create a stable, resilient community? This process is akin to finding scattered pieces of a shattered stained glass window. Individually, they are just colored shards, but when painstakingly reassembled, they reveal a magnificent, complex image. The reconstruction begins with the foundation, the environment itself, data on temperature from oxygen isotopes, precipitation levels from sediment grain size and mineralogy, and atmospheric CO2 from gas bubbles establish the stage's setting and climate. Then the players are introduced. Pollen and spores identify the plant life, painting a picture of the vegetation canopy, from the towering trees of a rainforest to the low-lying shrubs of a tundra. But this is more than a list of species. The relative abundance of different pollens can indicate the structure of the plant community. A diverse mix suggests a complex, multi-layered forest, while a dominance of one or two types might indicate a more fragile, monoculture-like environment. This floral census provides the base of the food web, the primary producers that capture the sun's energy. Next, the paleoecologists populate this world with its consumers. The microscopic shells of foraminifera and diatoms in marine cores, or the fragments of insects, mites, and even ancient DNA in terrestrial sediments, reveal the next trophic levels. The presence of certain beetle species, for instance, is a strong indicator of the types of decaying wood or animal carcasses that were present. By analyzing the stable isotopes of carbon and nitrogen preserved in the remains of these creatures, scientists can even trace their diets directly. A higher concentration of nitrogen-15 in a fossilized bone or shell indicates a higher position on the food chain. It's the chemical signature of a predator that has been eating other animals that have themselves been eating plants. This allows researchers to map out entire food webs, distinguishing between apex predators, mid-level herbivores, and tiny decomposers, understanding how energy was transferred and recycled through the entire system. A powerful example of this holistic approach comes from work done in the Amazon basin. Core samples extracted from lake beds and floodplains have revealed that the world's largest rainforest is not the unchanging, eternal jungle it appears to be. The pollen record shows that during past ice ages, when global temperatures were cooler and precipitation patterns shifted, the vast Amazonian rainforest actually contracted significantly. It was broken into isolated pockets or refugia, separated by vast expanses of dry savanna and grassland. This fragmentation had a dramatic effect on biodiversity. Species that required the dense, humid environment of the continuous forest were trapped in these shrinking islands, leading to accelerated evolution and speciation within the refugia, while other species adapted to the drier, more open conditions. This deep time perspective is crucial because it shows that the Amazon has faced dramatic change before, and that its incredible biodiversity is, in part, a product of that historical upheaval. It demonstrates both the resilience of life to adapt and its profound fragility when its habitat is fractured. These detailed reconstructions of past ecosystems are not just academic exercises, they provide critical baselines and models for understanding our future. By observing how ancient ecosystems responded to rates of change similar to those we are experiencing today, such as rapid warming or sea level rise, we can anticipate potential tipping points and vulnerabilities in our modern world. If we know that a certain type of forest ecosystem collapsed when temperatures rose by 2 degrees Celsius over 1,000 years, it gives us a sobering perspective on the potential consequences of achieving that same increase in just a century. Paleoecology offers us a library of natural experiments, showing us which communities are most resilient, which are most fragile, and how the complex web of life reassembles itself after a major disruption. It turns the scattered clues of the past into a vital guidebook, helping us to protect and steward the breathtakingly complex and interconnected biosphere we inherited. Yet for all their power, these geological archives are not infallible. Reading them is a complex art of interpretation, a delicate dance between the evidence we find and the countless ways it can be misunderstood or misrepresented. The first and perhaps most immediate challenge begins the moment the drill bit bites into the earth. The very act of extraction can disturb the pristine order of the layers. A core sample isn't simply pulled from the ground like a carrot from a garden. It requires immense force and mechanical vibration. This process can cause the delicate sediments to twist, fracture, or even undergo what's known as compaction, where the soft, waterlogged layers are squeezed, thinning them out and distorting their true thickness. In the worst cases, a section of the core can be completely lost, leaving a frustrating gap in the record where the drill simply failed to capture the material. It's like trying to pull a book from a tightly packed shelf and having several crucial pages tear out and vanish before you can read them. Even if a core is extracted perfectly, the record it contains may already be incomplete. The Earth's surface is a dynamic and often violent place. Periods of erosion can strip away entire chapters of history, scouring away layers that accumulated over millennia. Conversely, a hiatus or a period of non-deposition can mean that nothing was being laid down for a vast stretch of time, creating a silent gap in the timeline where no environmental data was recorded. A river might change its course, abandoning a floodplain and ending its sedimentary story there. A glacier might advance, scraping the bedrock clean of all previous sediment before beginning to deposit its own characteristic layer of chaotic till. These gaps are the maddening blank pages in Earth's diary, moments where the narrative simply stops, leaving scientists to infer what happened based on the chapters that come before and after. Then there is the problem of diagenesis, the chemical and physical changes that occur to sediment after it has been buried. Over millions of years, under the immense pressure and heat of overlying layers, the original minerals can dissolve and recrystallize. Pore waters can percolate through the sediment, leaching out some elements and depositing others, subtly altering the chemical signature. A shell that once precisely recorded the ocean temperature of its time might have its isotopic composition blurred or completely reset by this process. It's as if the ink on a historical document has run or faded, making the original words difficult or impossible to decipher. A scientist must therefore be a skilled detective, able to recognize the signs of this post-depositional alteration and distinguish the original environmental signal from the later chemical noise. Perhaps the most intellectually demanding challenge arises when different lines of evidence or proxies seem to tell conflicting stories. A layer in a core might contain pollen from cold-adapted tundra plants, suggesting a frigid climate, while the chemistry of the same layer, measured from insect remains, might indicate surprisingly warm temperatures. This isn't a failure of the science, it's a reflection of the incredible complexity of Earth systems. The discrepancy forces researchers to ask deeper questions. Was the local climate cold while global temperatures were actually warm? Did the plants respond more slowly to a rapid warming event than the insects did? Resolving these conflicts requires looking beyond a single core, correlating the data with other records from different locations, and applying sophisticated statistical models. This process of cross-validation is what separates robust, reliable science from mere speculation. It ensures that the final reconstruction isn't based on a single, potentially misleading clue, but on a preponderance of evidence from multiple, independent sources. This rigorous, self-critical approach is the true strength of the scientific method. By openly acknowledging these limitations and systematically working to overcome them, researchers build a much more nuanced and trustworthy picture of the past. They create reconstructions that are not simple, black and white cartoons, but rich, detailed portraits that acknowledge uncertainty and complexity. This intellectual honesty is what allows us to place our confidence in these stories from the deep past, knowing they have been tested and challenged at every turn, making the final narrative not weaker, but immeasurably stronger and more resilient. And as we stand on the shoulders of these monumental discoveries, the future of core sampling stretches out before us, gleaming with possibilities that would have seemed like pure science fiction just a generation ago. The next wave of technological innovation is set to transform this field once again, pushing the boundaries of what we can extract, analyze, and understand from these subterranean archives. Imagine drills that can operate with robotic precision in the most hostile environments on Earth, guided not by human hands but by sophisticated algorithms that can make real-time decisions thousands of feet below the surface. Automated drilling systems are already being developed that can work around the clock in the punishing cold of Antarctica or the crushing pressures of the deep seafloor, tirelessly retrieving pristine cores with minimal disturbance. These aren't just incremental improvements, they represent a fundamental shift towards continuous, high-fidelity data collection, allowing us to gather longer, more complete records from places we've only begun to scratch. But the revolution doesn't stop at the drill bit. The real magic will happen in the laboratory, where artificial intelligence is poised to become the ultimate research assistant. Picture an AI system trained on millions of geological and biological data points, capable of scanning a newly extracted core and instantly identifying subtle patterns, anomalies, and correlations that might take a human researcher months or even years to notice. These machine learning algorithms can process complex, multi-proxy datasets simultaneously, cross-referencing chemical signatures with fossil assemblages and sediment structures to generate holistic environmental reconstructions at a speed and scale we can barely comprehend today. This isn't about replacing scientists, it's about empowering them to ask bigger, more ambitious questions of the past, freeing them from the tedious grind of manual measurement to focus on the grand narrative. AI will help us see the invisible, detecting faint chemical traces of long-vanished ecosystems, or identifying the genetic shadows of unknown species from the merest fragments of environmental DNA. This analytical power will be supercharged by the discovery of novel biomarkers, entirely new classes of chemical and biological signatures that act as proxies for environmental conditions we currently struggle to measure. Researchers are already exploring the potential of lipid biomarkers, the durable remains of cell membranes from ancient bacteria and archaea, which can reveal incredibly specific information about past temperatures, pH levels, and even the salinity of ancient waters. Other scientists are delving into the world of isotopic systems beyond oxygen, such as clumped isotopes, which can provide temperature readings that are completely independent of the composition of ancient seawater, sidestepping a major source of uncertainty in current models. These new tools will allow us to move beyond broad-stroke climate reconstructions and into the realm of hyper-specific detail, understanding not just the average annual temperature of a period, but its seasonal variability, its storm frequency, and even the chemistry of individual rainfall events. The targets for these next-generation tools are as ambitious as the technology itself. In Antarctica, international consortia are planning missions to hunt for Earth's oldest ice, drilling down to regions where the ice may be a staggering 1.5 million years old. This quest isn't just about breaking a record, it's about reaching back to a pivotal moment in Earth's climate history known as the mid-Pleistocene transition, when the planet's ice age cycles mysteriously shifted from occurring every 40,000 years to every 100,000 years. The ice from this period could hold the secret to why this shift happened, offering a crucial key to understanding the long-term stability of our climate system. Even more audaciously, projects like the Japanese-led Chikyu expedition aim to do what has never been done before: drill all the way through the Earth's crust and into the upper mantle. While their primary goal is to understand tectonic processes and earthquake genesis, the cores they retrieve will be invaluable archives of oceanic conditions and microbial life from the most extreme environments on the planet, potentially rewriting our understanding of the limits of life itself. These advancements are not merely academic pursuits. They are urgently needed to inform our response to the most pressing global challenges of our time. The higher resolution climate records will allow us to refine our models, giving us a much clearer picture of how fast sea levels can rise, how abruptly ocean currents can shift, and how quickly ecosystems can collapse under pressure. This isn't just about predicting the future. It's about understanding the precise mechanisms of change, allowing us to identify potential tipping points before we cross them. In the realm of resource management, the ability to read the chemical history of sedimentary basins with greater clarity will revolutionize our search for critical minerals and rare earth elements essential for renewable energy technologies, all while minimizing the environmental footprint of exploration. The future of core sampling is a future of deeper knowledge, sharper insights, and a profoundly expanded ability to listen to the stories our planet has been waiting for millions of years to tell. This incredible power to reach into the past, however, comes with a profound and growing responsibility. As we develop ever more sophisticated ways to analyze these cores, we are forced to confront a fundamental truth: these geological archives are not infinite. Every core sample extracted from the Earth is a unique, non-renewable resource, a one-of-a-kind chapter from the story of our planet. Once a section of core is consumed by a destructive testing method, ground up for isotopic analysis or dissolved to extract ancient DNA, that specific piece of the record is gone forever. It cannot be re-drilled. This reality places a tremendous ethical burden on the scientific community to act not just as researchers, but as conscientious curators for future generations. The knowledge we can gain today must be carefully balanced against the knowledge we might preclude tomorrow, when analytical techniques we cannot yet even imagine could extract entirely new stories from the very same material. To navigate this delicate balance, the global scientific community has established rigorous international protocols and infrastructure. Major drilling programs like the International Ocean Discovery Program operate under strict guidelines that treat every meter of core as a precious library book, not a consumable lab supply. When a core is retrieved, it is immediately carefully described, photographed, and scanned using non-destructive techniques like CT scanning to capture as much data as possible without altering the sample. It is then split lengthwise. One half, the archive half, is meticulously preserved in a climate-controlled repository, a library of the Earth where it is kept intact for future study. The other half, the working half, is made available for researchers around the world to request small subsamples for their specific, destructive analyses. This system of sharing and centralized curation ensures that the core is not wasted by duplicate studies and that the most valuable material is protected in perpetuity, a gift of knowledge passed from one generation of scientists to the next. The ethical considerations extend far beyond the sample itself to the very act of extraction. Drilling a deep ice core in the pristine wilderness of Antarctica or a sediment core in a protected national park is an invasive procedure. It requires heavy equipment, logistical support, and leaves a permanent, albeit small, scar on the landscape. The decision to drill in these sensitive environments is never taken lightly. It involves extensive environmental impact assessments, consultations with local and indigenous communities, and a commitment to minimize the footprint and restore the site as completely as possible. The scientific value of the knowledge gained must demonstrably outweigh the temporary disruption to the ecosystem. This is a constant calculation, a weighing of immediate gain against long-term preservation, ensuring that our quest to understand the planet's history does not come at the cost of damaging its present. This ethical framework also encompasses culturally significant sites. A lakebed that holds a climate record might also be a sacred site for an indigenous community. Sediments that contain evidence of ancient human habitation are themselves archaeological treasures. Responsible coring in these contexts requires a deeply collaborative approach, working directly with descendant communities and cultural heritage experts. This collaboration ensures that drilling proceeds with respect, that any cultural material is handled appropriately, and that the resulting knowledge benefits and is shared with the communities most connected to that land and its history. It transforms the process from one of extraction to one of partnership, recognizing that the stories locked in the earth belong to all of humanity and must be uncovered with care, humility, and a deep respect for the myriad ways we value our shared past. Perhaps the most compelling testament to this collaborative power lies in the story of Doggerland. For centuries, fishermen in the North Sea occasionally hauled up strange artifacts in their nets: antler points, stone tools, and even animal bones from long-extinct species. These were curious anomalies, isolated finds with no context. It was only when geologists, climatologists, and archaeologists finally sat down together, pooling data from thousands of seafloor sediment cores, that these fragments coalesced into a lost world. The geologists mapped the ancient river channels and coastlines from sediment grain sizes. The climatologists used pollen and isotope data from those same cores to reconstruct the vegetation and climate. The archaeologists then placed those human artifacts directly onto this resurrected landscape, understanding for the first time that these tools were not lost at sea, but dropped on dry land by Mesolithic hunters stalking herds of deer across a vast, low-lying plain. No single discipline could have painted this picture alone. It was the fusion of their distinct perspectives that brought a sunken continent back to life. This synergy extends into the very building blocks of life through the burgeoning field of paleogenomics. Imagine a biologist extracting a sample of mud from a core taken from an ancient lakebed. To a geologist, it's just a layer of silt, but the geneticist working alongside them can filter that mud to find minuscule fragments of environmental DNA genetic materials shed by every plant, animal, and microbe that once lived in and around that lake. By sequencing this genetic debris, they can identify the species present at that exact moment in the core's timeline. Now, combine that with the climatologist's data on a sudden temperature drop from the same layer. Together, they can tell a story not just of climate change, but of a biological response, how the ecosystem shifted, which species declined, and which new cold-adapted organisms moved in. The core sample transforms from a climate log into a genetic time machine, revealing evolutionary dramas that left no fossil record. This cross-pollination of ideas constantly challenges and refines established theories. A classic example is the debate over the extinction of North America's megafauna creatures like mammoths and giant ground sloths. For a long time, the dominant theory pointed to human hunting as the primary cause. But when archaeologists studying layers with human artifacts and animal bones began collaborating with climatologists analyzing high-resolution climate records from ice and sediment cores, a more complex picture emerged. The cores showed a period of immense climatic instability right as humans arrived, with rapid warming and cooling swings that would have placed enormous stress on habitats. The story was no longer a simple one of overhunting. It became a nuanced narrative of a perfect storm, where a vulnerable ecosystem was hit simultaneously by a rapidly changing climate and a new, efficient predator. This interdisciplinary dialogue prevents science from settling into easy answers, forcing a richer, more evidence-based understanding of cause and effect. The ultimate value of this collaborative model is its ability to generate truly holistic narratives that resonate far beyond the laboratory. A story woven from threads of geology, biology, and climate science is not just more accurate, it is infinitely more human. It allows us to understand the world as an interconnected system, to see how a shift in ocean currents could alter rainfall patterns on a continent, which would change the vegetation, which would force human migration, which would influence culture and technology. This is the difference between a list of facts and a compelling story. It's what transforms a graph of temperature fluctuations into an epic tale of survival, adaptation, and resilience. By breaking down the walls between scientific silos, researchers are not just sharing data, they are co-authoring the grandest story ever told, the complete biography of our planet, offering profound insights that no single field could ever hope to achieve in isolation. Yet for all the profound insights they offer, these stories from the deep past remain locked away if they stay confined to research papers and academic conferences. The true power of this knowledge is only unleashed when it is shared, when the incredible narratives held within core samples are translated into experiences that captivate, educate, and inspire the public. This vital work of translation happens in the dynamic spaces where science meets society, in the hushed halls of museums, the sweeping visuals of documentaries, and the hands-on participation of citizen science. These initiatives do more than just communicate facts. They build bridges of understanding, connecting people emotionally and intellectually to the epic history of their planet, and empowering them with the context needed to face its future. Museums are perhaps the most powerful places for this kind of encounter, transforming abstract data into tangible wonder. Imagine walking through an exhibit and coming face to face with an actual ice core, a gleaming cylinder of ancient ice that's been carefully preserved in a specially designed freezer display. You can see the individual layers, the subtle bands of light and dark that represent annual snowfall from a time when woolly mammoths still walked the earth. This isn't a model or a picture, it's the real thing, a physical piece of a vanished age. Nearby, an interactive touchscreen might allow you to virtually core into a digital landscape, watching as the layers peel back to reveal a swampy carboniferous forest teeming with giant dragonflies, then a shallow Silurian sea, and finally the bare rock of a primordial volcano. This kind of display does what a textbook never could. It makes deep time visceral, allowing visitors to grasp the staggering scale of geological history, not as a number, but as a feeling, a moment of awe that ignites a lasting curiosity. Documentary filmmakers wield a different kind of magic, using the power of visual storytelling to transport audiences directly into these lost worlds. Through sophisticated computer-generated imagery, we don't just hear about the asteroid impact that ended the reign of the dinosaurs. We witness it from the perspective of a triceratops, feeling the ground shake and seeing the sky darken with apocalyptic fury. We can dive into the warm, shallow seas of the Devonian period, swimming alongside bizarre and ancient fish, or soar over the vast, grassy plain of Doggerland, watching as small bands of Mesolithic hunters track their prey. These narratives are grounded in the real data from core samples, the pollen, the isotopes, the microfossils, but they translate that data into immersive, emotional experiences. They show the process of science too, following the teams of researchers as they battle polar blizzards to retrieve an ice core or work through the night on a drilling ship in a storm-tossed sea. This demystifies the scientific process, revealing it as a grand, human adventure driven by curiosity and perseverance, making viewers feel invested in the discoveries themselves. Perhaps the most engaging development in public science is the rise of citizen science projects that invite everyone to participate in the discovery process. Online platforms now allow anyone with an internet connection to help paleontologists classify microfossils from sediment cores, or to trace and count the annual layers in high-resolution images of ice cores from the comfort of their own home. These are not simple games. They are real research projects that leverage the pattern recognition skills of thousands of volunteers to process data at a scale that would overwhelm a small team of scientists. This creates a powerful sense of shared ownership and contribution. A retiree in Florida or a student in India can rightly say they helped identify a key volcanic ash layer or contributed to a timeline of ancient climate change. This active participation transforms people from passive recipients of information into active collaborators, fostering a deeper connection to the scientific endeavor and a more personal stake in its findings, especially when those findings relate to urgent modern issues like climate change. Ultimately, this entire ecosystem of engagement, from museum dioramas to virtual reality experiences, serves a higher purpose, grounding our understanding of contemporary environmental challenges in the deep time context they require. It's one thing to be told that the climate is changing. It's another entirely to see a graph that plots the relatively stable, sawtooth pattern of ice age cycles from an ice core over hundreds of thousands of years, and then to see the current spike in carbon dioxide and temperature rocket off the chart. completely detached from any natural precedent. This visual, derived directly from core sample data, makes the unprecedented nature of modern climate change undeniable and instantly comprehensible. By connecting the dots between past extinctions, ancient greenhouse worlds, and the fragile stability of our own interglacial period, these public education initiatives do more than just inform, they motivate. They turn abstract concern into informed advocacy and foster a sense of collective stewardship for a planet whose incredible history we are only just beginning to appreciate, ensuring that the lessons from the deep past guide our actions for the future. But all of this meticulously gathered data, the isotope ratios, the pollen counts, the magnetic signatures remains a collection of abstract numbers and descriptions until it undergoes a remarkable transformation. This is where the true artistry of geological reconstruction comes into play in the powerful field of scientific visualization. Think of it as the process of translating a dense, complex novel written in a forgotten language into a breathtaking, immersive film. Specialized software and modeling tools act as the directors and cinematographers, taking the raw numerical scripts provided by the core samples and turning them into vivid, moving pictures of worlds that have been lost to time. One of the most foundational tools in this endeavor is Geographic Information Systems, or GIS. At its core, GIS is a digital cartographer's dream, but its power goes far beyond simply drawing maps. Scientists can input thousands of data points from core samples drilled across a continent, each with its own latitude, longitude, depth, and a suite of environmental proxies, and the software can interpolate between them. It can take a measurement of ancient sea surface temperature from a core in the North Atlantic and another from the South Atlantic, and generate a smoothed, color gradient map of the entire ocean's temperature at that specific moment in the past. The same can be done for precipitation levels, vegetation types, or ice sheet thickness. Suddenly, a spreadsheet of numbers becomes a dynamic, visual climate model, allowing researchers to watch as entire continents turn from green to brown during a drought or see the pulse of a warm current as it shifts course over millennia. For even more dramatic and intuitive storytelling, paleogeographic modeling software takes this a step further into the realm of three-dimensional animation. These programs can use the data to digitally rebuild the very topography of the ancient world, dropping sea levels to reveal land bridges, eroding mountain ranges that have long since vanished, or flooding continental shelves to recreate ancient seaways. The most sophisticated models don't just show a static snapshot, they animate the entire process. You can witness the supercontinent of Pangaea not as a static image in a textbook, but as a living, breathing entity beginning to rift apart in a slow-motion explosion. You can see the continents creep towards their modern positions. Watch as the Isthmus of Panama slowly rises from the sea to permanently alter global ocean circulation, or observe the incredible cycles of ice ages, with massive glaciers advancing and retreating across North America and Europe like a slow, powerful tide. This power to visualize the past does more than just create pretty pictures. It serves a crucial scientific purpose by revealing patterns and connections that might otherwise remain hidden in spreadsheets. A researcher might have a theory about how the closing of an ancient ocean gateway affected regional rainfall, but seeing that process play out in an animated model can immediately confirm or refute the idea, making the invisible linkages between tectonics and climate starkly visible. It allows for a form of scientific testing where different variables can be adjusted in the model to see which scenario most accurately reproduces the evidence found in the actual core samples. This iterative process of going from data to model and back to data again refines our understanding and builds ever more accurate reconstructions. Perhaps the most profound impact of this visualization art is its ability to engage and educate far beyond the scientific community. An animated map showing the dramatic exposure of the Bering Land Bridge during the last ice age, creating a migration corridor for humans and animals between Asia and North America, conveys a concept more instantly and memorably than any paragraph ever could. A 3D fly-through of the swampy, oxygen-rich coal forests of the Carboniferous period, with its giant insects and towering club mosses, creates an emotional and intellectual connection to deep time that is simply unforgettable. These visuals bridge the formidable gap between complex data and human experience, transforming abstract findings into stories we can see and feel, making the incredible saga of our dynamic planet accessible to everyone. This long-term perspective is arguably the most critical contribution of core sample science to the modern climate crisis. It provides the essential baseline, the planetary vital signs, against which our current situation can be accurately diagnosed. When we look at the ice core record, we see a very clear, natural rhythm, a sawtooth pattern of gradual cooling into ice ages, followed by sharper warming into interglacial periods like the one we've enjoyed for the past 11,700 years. The driver of this rhythm is a complex dance of subtle changes in Earth's orbit and tilt, known as Milankovitch cycles. What's stunningly clear from the ice cores is how tightly and consistently temperature and greenhouse gas concentrations have moved together in lockstep with these orbital changes over the past 800,000 years. Carbon dioxide levels have naturally oscillated between about 180 parts per million during ice ages and around 280 parts per million during warm interglacials. This historical range establishes the planet's normal operating parameters for this current geological epoch. Now place our current reality on that same graph. Instead of 280 parts per million, we have skyrocketed past 420 parts per million of carbon dioxide in the atmosphere, a level not seen on Earth for several million years, long before the advent of humans. Even more alarming than the sheer concentration is the rate of change. The natural shifts between ice ages and interglacials, which typically involved an 80 to 100 part per million change in CO2, unfolded over thousands of years. This gave ecosystems and sea levels vast stretches of time to adapt and migrate. Our current spike of over 140 parts per million has occurred almost entirely since the Industrial Revolution, a geological instant. The ice core record shows us, beyond any doubt, that the speed and magnitude of this change are utterly outside the bounds of natural variability. We are conducting a radical, uncontrolled experiment on the global climate system with no precedent in the entire history of human civilization. Beyond simply diagnosing the problem, core samples are invaluable for predicting the future by revealing how the Earth system responds to forcings. They act as a library of past climate experiments, showing us the consequences of releasing vast quantities of greenhouse gases. One of the most instructive periods is the Paleocene-Eocene thermal maximum, or PETM, which occurred about 56 million years ago. Sediment cores from this time tell a story of a massive, rapid release of carbon, possibly from methane hydrates on the ocean floor or volcanic activity. The result was a global temperature increase of 5 to 8 degrees Celsius, major ocean acidification that dissolved the shells of deep-sea organisms, and a significant reshuffling of life on land and in the seas. While the PETM was likely driven by natural causes and unfolded over a few thousand years, still much slower than today's release, it serves as a powerful analog. It shows us the kind of profound, long-lasting changes that can be triggered by a large carbon pulse, giving us a sobering preview of the planetary trajectory we are on if emissions continue unabated. This deep time data is crucial for identifying tipping points, those critical thresholds in the climate system which, once crossed, can trigger irreversible changes. Ice and sediment cores reveal that Earth's climate doesn't always change in a smooth, linear fashion. It can flip abruptly from one stable state to another. We see evidence of these flips in the past, such as the sudden cold snaps within ice ages called Dansgaard-Easter events, where Greenland temperatures shot up by 10 degrees Celsius in just a few decades. By studying the conditions that preceded these abrupt shifts, scientists can better understand the vulnerabilities in our current system. Are we approaching a tipping point that could shut down the Atlantic meridional overturning circulation, which governs European weather? Could we trigger a massive release of methane from thawing permafrost, creating a devastating feedback loop? Core samples don't give us exact answers, but they provide the only available evidence of how the system has behaved under stress before, allowing modelers to refine their predictions and policymakers to understand the stakes of inaction. This is where the abstract science translates directly into concrete policy and stewardship. The evidence from cores is not locked away in academic journals. It forms the foundational bedrock of reports by the Intergovernmental Panel on Climate Change. When the IPCC states with high confidence that human influence has warmed the atmosphere, ocean, and land, it is relying on the long-term context provided by paleoclimatology. This evidence informs everything from international climate agreements that set emission targets to national strategies for building resilient infrastructure and transitioning to renewable energy. It moves the conversation from a theoretical debate about a changing climate to an evidence-based imperative for rapid decarbonization. By showing us the profound consequences of past warming events, core samples make the case that mitigating climate change is not an environmental luxury, but a fundamental necessity for preserving the stable planetary conditions that allowed our civilization to flourish in the first place. They transform geological history from a story about the distant past into the most urgent guidebook we have for securing our collective future. For all the breathtaking clarity core samples have brought to our understanding of Earth's history, they have also unveiled a host of profound and tantalizing mysteries. These archives don't just provide answers, they ask even bigger questions, revealing gaps in our knowledge and anomalies that defy easy explanation. One of the most perplexing enigmas lies in the triggers for the most abrupt climate shifts. We can see the stark evidence of these events, like the dramatic temperature swings during the Younger Dryas period, recorded with perfect clarity in the ice. We can see the what and the when with astonishing precision, but the ultimate why remains fiercely debated. Was it a sudden influx of freshwater from melting ice sheets that shut down the ocean's conveyor belt circulation? Could it have been a comet impact or a series of volcanic eruptions that tipped the balance? The cores show us the effect in vivid detail, but the initial cause often remains just out of reach, a ghost in the machine of Earth's climate system that we are still trying to identify. Similarly, the exact causes and mechanisms behind the planet's great mass extinctions continue to be refined and argued over. The iridium layer in the sediment cores is the smoking gun for the asteroid impact that ended the age of the dinosaurs, but that impact alone may not tell the whole story. Cores from that time period also show evidence of massive, long-lasting volcanic eruptions in India, known as the Deccan Traps, which would have been pumping enormous quantities of gas and ash into the atmosphere for thousands of years. So did the dinosaurs succumb to the immediate cataclysm of the impact, or were they already weakened by the environmental degradation caused by the volcanoes? Or was it a devastating 1-2 punch from both events? The core samples provide the physical evidence of these twin catastrophes, but untangling their individual contributions to the extinction event is a complex forensic puzzle that scientists are still piecing together. Beyond these grand events, the records are also filled with smaller, unexplained anomalies that hint at processes we don't yet understand. A layer of sediment where the chemical proxies for temperature seem to conflict with the biological ones. A sudden, short-lived spike in a rare element with no obvious source. An isotopic ratio that doesn't match any known geological process. These tiny irregularities are the loose threads in the tapestry of Earth's history, suggesting that there are forces and reactions at work, perhaps even entirely unknown cycles that we have not yet discovered. They remind us that for all we have learned, our planet still holds deep secrets, and the models we use to explain the past are still works in progress, constantly being updated with each new discovery. This is precisely why the scientific quest is far from over. It is merely entering a new and even more exciting phase. The next great discoveries will likely come from drilling in the most extreme and unexplored frontiers of our planet. Projects are already underway to probe the hidden worlds beneath the ice sheets. Subglacial lakes like Lake Vostok in Antarctica have been sealed off from the atmosphere for millions of years. Drilling into the sediments at the bottom of these pristine, alien environments could reveal a completely unknown history of the Antarctic continent, and perhaps even unique forms of life that have evolved in total isolation. Elsewhere, the sites of ancient asteroid impact craters are prime targets, while we have the layer of debris from the Chicxulub impact. Drilling directly into the crater's center could provide a minute-by-minute record of the impact's aftermath, revealing how life in the immediate vicinity recovered or failed to recover from the most disastrous day in our planet's history. These unanswered questions are not a sign of scientific failure, but the very engine of scientific progress. They are the compelling mysteries that drive researchers to endure the brutal cold of the poles and the pitching decks of drilling ships. Every new core pulled from the ground is a potential Rosetta Stone, a single sample that could contain the key to unlocking one of these deep time riddles. It is a powerful reminder that Earth's history is not a closed book, but a living narrative that we are actively helping to write with every meter of rock and ice we recover. The pursuit is fueled by a fundamental human curiosity, a desire to look back into the deep past not just to understand where we came from, but to see the full range of possibilities for where we and our planet might be headed in the future. Core samples are so much more than just cylinders of rock and ice. They are nothing less than portals to forgotten worlds, offering us a direct line to the epic story of our planet's dynamic history. We've journeyed together through the remarkable ways these geological archives allow us to reconstruct ancient climates, from the ice ages that gripped the globe to the warm periods that saw forests growing at the poles. We've used them to map lost landscapes like the sunken continent of Doggerland, and to witness the profound and lasting impact humanity has had on the environment, from the lead smelting of the Roman Empire to the atomic age's radioactive signature. These slender columns of Earth hold the answers to some of our biggest questions about where we came from, and provide critical context for the immense challenges we face in the future. As we piece together this shattered puzzle of our primeval Earth, each core sample adds another fragment to the picture, but the true value is far greater than the sum of these parts. The knowledge we gain is profound, but it's the perspective that is truly transformative. This deep time view allows us to see our current moment not as an isolated point, but as a single frame in a movie that has been playing for 4.5 billion years. It shows us that change is the only constant, that stability is fleeting, and that our modern world is the product of an unimaginably long and complex series of events, accidents, and cycles. This perspective is humbling, but it is also empowering, grounding us in the reality of our planetary home and our responsibility within it. Let this journey inspire you to look at the ground beneath your feet with a new sense of wonder. That soil, that bedrock, is not just dirt and stone. It is an archive, a library holding the memories of everything that came before. The next time you see a road cut revealing layers of rock, or a cliff face showing stripes of different colors, remember that you are looking at the pages of Earth's diary, waiting for a curious mind to read them. Keep asking questions, keep seeking out the mysteries, and never lose that sense of awe for the intricate and beautiful tapestry of time that has been woven right below us, just waiting to be discovered. We would love to hear which part of this deep time detective work fascinated you the most, so share your thoughts in the comments below. If you enjoyed this exploration into history's greatest mysteries, make sure to subscribe and hit the bell so you don't miss our next adventure. Thank you for watching, and as always, keep wondering.